there is a connection between simple harmonic oscillator motion and rotational motion. If you look at the animation, you will notice that the green dot in the center of the red oscillating square on the spring is in the same vertical position as the green dot that's going around the circle. So if you look at the Y position of the green dot going around the circle, it's exactly the same as the Y position of the center of the block that is undergoing simple harmonic oscillator motion. The Y component of the motion of the green dot going around the circle would also be the same as simple harmonic oscillator motion if you had a horizontal spring and block oscillating in the horizontal direction. So both the X and Y components of the rotational motion mimic simple harmonic oscillator motion. We can use this to figure out some useful information about the period of simple harmonic oscillator motion, how much time it takes for the block to undergo one complete oscillation. So first off, if we make this comparison between this green dot going around the circle and the motion of the mass on the end of the spring, we'll notice that the X position of the dot is the same as the position of the mass on the spring. Another way of thinking of that is that if we imagine shining a light from above down on this ball, then the ball would cast a shadow that would move right along with the mass on the end of the spring. So if we think about the ball going around the circle, the tangential velocity, which is the velocity of the ball moving around the circle, is equal to the distance that the ball travels in one complete orbit, which would be 2 pi times the radius of that circle, A, divided by the amount of time it takes to go around once, or the period of that motion. If we solve this equation for the period by rearranging it, we see that the period would be 2 pi A over the speed going around the circle. Now if we switch our attention to the mass on the spring, we can compare two positions in its oscillation and conserve total mechanical energy. So we're assuming there is no friction in this situation. So we can compare when the mass is out here and it's a distance A away from the equilibrium position. If we assume that this is the maximum position that the mass can be from the center, then the total mechanical energy will be 1/2 Ka squared, that's the spring potential energy, because at this point the mass is turning around and its velocity is 0. Then that will be equal to 1/2 mv squared when the mass is at the equilibrium point, because here the spring is not stretched, there is no spring potential energy, all of the energy is kinetic energy. And at this point, the block will be moving with the same velocity as the dot going around the circle when it's at either the apex and going this way, or when it's at the bottom of the circle and going this way. So the speed of the block and the dot going around the circle is in the x direction is the same at these 2 points. So we can say that that's equal to 1/2 mv naught squared, where this is the speed of the dot around the circle. So if we rearrange this equation, we can rearrange it so that we have a squared divided by v naught squared, the 1/2 would cancel, and we would have that would be equal to a ratio of m over k. Then we could take the square root of both sides and find that a over v naught is equal to the square root of m over k. But then we notice that in our expression for the period, that we have an a over v naught, and we can replace that then with the square root of m over k. So we find that the period of oscillation for our mass on the spring is equal to 2 pi times the square root of m over k. So we can see that we've made a very useful observation by equating the motion of the dot going around the circle and the mass oscillating back and forth on the spring. that's allowed us to find the period of the mass on the spring using only simple harmonic oscillator quantities, using only the amount of the mass and also the spring constant. And then that's equal to, and then that expression is equal to the period, the amount of time for one complete oscillation. Once we know the period, it's easy to find the frequency of oscillation, how many full oscillations occur in 1 second, by just taking the inverse of the period, and we find we get this expression here. Then we can also find the rotational speed of the ball going around the circle, and this is a quantity that's also known as the angular frequency, and the angular frequency is always 2 pi times the ordinary frequency, how many full oscillations or complete trips around the circle that the ball takes, 2 pi times that frequency, which is equal to the square root of k over m. So the angular speed of the ball going around the circle is equivalent to something called the angular frequency of oscillation for the mass on the spring. So we can use that then to come up with a convenient expression describing the horizontal position of the mass on the spring that is a function of time instead of looking for where the position is in terms of maybe the acceleration or something else. So the position of the horizontal position of the ball, and therefore also the horizontal position of the ball's shadow, which we said was the same as the horizontal position of the mass on the spring, that horizontal position is equal to this x component of this triangle, where the hypotenuse is a, the radius of the circle, and then the x component is adjacent to that, is the side adjacent to this angle, and so we can say that the x component is a times the cosine of theta. But theta, thinking back to our equations for angular motion, we know that the angular displacement is equal to omega t plus maybe some initial starting angle. So this was the equation for angular displacement that we looked at when we were looking at motion around a circle. And so we found that we could write angular displacement for constant angular velocity as omega times t, and then we might have some initial starting angle that we have to use as well to find that initial angular position. And then we can write omega as being equal to the angular displacement with time. And if we look at one full rotation, then we have an angular displacement of 2 pi radians divided by the amount of time it takes to complete one full rotation, which is equivalent to 2 pi f. And so that's where this relationship comes from. But then we can take this equation here for the x position of both the ball and the mass on the end of the spring and use that to find equations that describe the motion of simple harmonic oscillation. So if we have this mass that's bouncing up and down, undergoing simple harmonic oscillation, if we look at the line that it draws on this continually scrolling piece of paper, we can see that that line would make a sine wave. And so we can write down sine or cosine, which is just a shifted sign, equations that describe the position, the velocity, and the acceleration of the mass on the end of the spring. So in any of those cases, we see that there is a trigonometric function, and then we have an amplitude that tells us what the biggest, that the position, what's the biggest the velocity, and what's the biggest that the acceleration gets. And we see that these are a function of time, so they change with time. And also to write down these equations, we need to know the frequency of the oscillation and maybe something about the starting angle. So it's an interesting thing that you can calculate the magnitude of the velocity. So what's the maximum velocity? The amplitude of the velocity is equal to the amplitude of the position times the angular frequency, and the amplitude of the acceleration, which is this, it's the thing that multiplies the trigonometric function, is equal to the amplitude of the position times omega squared. Now, one further note about these equations. If you're using these equations to find the position, velocity, or acceleration of an oscillating mass at some specific time, one thing to be aware of is that you have an expression inside these parentheses, and this expression gives you an angle in radians. So if you are using these equations, your calculator must be in radian mode in order to calculate the sines and the cosines of these expressions, because you have an equation here that is in radians. So let's look at an example problem where we take a look at some of this information that we have learned about the period of oscillation and the equations of motion for oscillation. So in this first example, we have an object attached to a spring and its frequency of oscillation is measured. Then another object is connected to the first and the resulting mass is 4 times the original value. So by what factor would the frequency of oscillation be changed? So if we're looking at this problem, the piece of information that we have is that we know that the final mass, so mass final, is equal to 4 times the initial mass. So initially we had a frequency of oscillation which is equal to 1 over 2 pi times the square root of k, the spring constant, divided by the initial mass. So this is the equation that we saw on the previous slide where you can use mass to figure out the frequency of oscillation. So likewise, the final frequency, is going to be equal to 1 over 2 pi times the square root of k over m final. But we know that m final is 4 times m initial. And we can break this up, this stuff under the square root, we can also write that as the square root of 1/4 times k over m initial. So then we can also use the property that if you have the square root of a times b, that's the same thing as the square root of a times the square root of b in order to break up this square root. So that's going to be equal to 1 over 2 pi times the square root of 1/4 times the square root of k over m initial. So if we take the square root of a quarter, that's going to be the same thing as taking the square root of 1 divided by the square root of 4. So that's going to give us 1/2 times 1 over 2 pi times the square root of k over m initial. And the stuff in the parentheses here, well, that's just the same thing as the initial frequency. So that's the initial frequency. So what we've just shown is that the final frequency is going to be equal to 1/2 the initial frequency. So the factor that the frequency of oscillation has changed by is 1/2. So our final frequency is 1/2 of the initial frequency. So next let's look at this example problem. A mass on a spring vibrates in simple harmonic motion at a frequency of 4 Hertz and an amplitude of 4 centimeters. If a timer is started when its displacement is at maximum, so that means x equals 4 centimeters when t is equal to 0, what is the acceleration magnitude when t is equal to 3 seconds? So if I write down some of the information that I'm given, I know that we have simple harmonic motion at a frequency of 4 Hertz. So the frequency is 4 hertz. That means there's 4 complete oscillations every second. And the amplitude of this motion, so this is the position amplitude. I'll write a sub x. So the position amplitude is 4 centimeters. And we also know that the position is equal to 4 centimeters when the time is equal to 0. So those are the pieces of information that were given in the problem. So if we write down our expression for the acceleration, we see from the previous slide that acceleration, which is the thing we want to find, is equal to the negative of ax times omega squared times cosine of 2 pi times frequency times time plus the initial angle, the starting angle. So if we look at this information that we need to find the acceleration, we have the position amplitude. So the position amplitude is 4 centimeters. We have omega because omega is equal to 2 pi times the frequency, and we're given the frequency is 4 hertz. So then we have cosine 2 pi f, and we want to find the acceleration when the time is equal to 3 seconds. So we know what time we want to use, but we don't know this initial starting angle. So we're going to have to figure that out first. But we do have the piece of information that x is equal to 4 centimeters when t is equal to 0. So our equation for the position of this mass is equal to ax cosine 2 pi frequency times time plus the starting angle. And here we know that when time is equal to 0, we know ax and we know the position, so that should allow us to find that starting angle. So if we put that information in, we know that x is at 4 centimeters when t is equal to 0. So x is at 4 centimeters, so that's 0.04 meters, is equal to 0.04 meters times the cosine of 2 pi times the frequency times time, but time is 0, so all of this stuff is going to be equal to 0, plus the starting angle. So to solve for this starting angle, we can first divide both sides by 0.04 meters, so that's going to cancel. And so we have 1 is equal to the cosine, this stuff is all 0, so cosine of theta naught. So then we need to take the inverse cosine, and if we take the inverse cosine, or we remember that when is the cosine equal to 1? Well, the cosine is equal to 1 when theta is equal to 0. So that means that theta naught is equal to 0. So now we have all the information we need to solve our problem, to solve for the acceleration and find the magnitude of the acceleration when t is equal to 3 seconds. So then we can just, I think, plug in numbers to our acceleration formula. So we have a is equal to minus this is the position amplitude. So the position amplitude is 0.04 meters. And then omega is 2 pi times the frequency, which is 4 hertz. Now, 4 hertz, that can also be written as 4 times 1 over seconds, because it's cycles per second. So 2 pi times 4 hertz, and this quantity all gets squared, times the cosine of 2 pi times the frequency, which was 4 hertz, times the time, and the time was 3 seconds that we're interested in, and then plus omega naught, but this was equal to 0. Omega naught's equal to 0. So then we can take the cosine of this, and we have to remember that The calculator must be in radian mode because this is going to give us an angle in radians. So we have to use radian mode, and then we can do this calculation. And if we do that, we find we get an amplitude equal to negative 25.3 meters per second squared. So here's where the meters comes from, and the hertz is the same as 1 over seconds, and then that gets squared. So negative 25.3 meters per second squared. The question asks for the magnitude. So the magnitude, the amount of acceleration, which would be a positive number, is 25.3 meters per second squared. So next, let's look at this question. If the amplitude of a system moving in simple harmonic motion is doubled, which of the following quantities doesn't change?